right. So granted, today is not the 8th. You know that correctly today. So anyway, I'm Dennis, and I am a researcher at the University of Helsinki. Data science background, and my research is in MLOps, which is the topic of today, but I particularly study deployment of machine learning systems. That's my focus area. And I think all the talks that we've had today have been quite excellent in trying to set the stage for my presentation today. All of them. I think what I bring now is evidence from the industry, because this study is based on interviews with practitioners from different companies, as I will show. So it's an empirical study. So what we will see here is basically hardcore implementations of the tools that are used compared to all the things that have been spoken by Patrick and also Emmanuel. So what Emmanuel has spoken about, what Patrick has spoken about, I'll basically be trying to qualify that based on how I have seen industry experts actually do things. And feel free to ask questions as we go along. So the talk is based on a paper that we published in IEEE. That's the ID of the paper, so if you go in there, you should be able to access it. I'll just gloss through it. Or you can, and it's open access, so it's freely available to you if you want to read that. So the setting is that it's all based on Finnish companies. The companies are growth startups and very large companies also in the study. $49 billion in revenue, 100,000 euros in revenues for the small companies. So quite a wide range of companies covered here. Maybe I should have already gone into the companies. The companies that I'm talking about present a lot of things in terms of where they operate. If you look at the domain in terms of the business sectors they intend to operate on, they vary quite a lot, from finance to pharmaceutical companies, companies that are dedicated in making IoT solutions, healthcare sector, and so on. Here we try to show generally where does the data come from for the machine learning systems that are built. The data is sourced from internal systems, as we heard in the case of Relex. In some cases, data is coming from real sensors seated in buildings or in cars or things like that. But a large share of them are basically built from internal systems. If you look at sort of the systems that are represented here, I will basically try to highlight 50% of these are neural network based, and then you have another 50% that are not neural networks, so they're based on basically classic machine learning, circuit models and things like that. So these are the case companies, and why do we study these things, or why did we see it necessary to study this? I'll go back up. For those who have been in academia or taken courses, you probably know this paper by Scarlett. This guy is quite renowned guy from Google. And what the paper presents is that he talks about hidden technical debt in machine learning. So he presents the case that machine learning tends to be a very small part of what you do in practice. But a large part of what you end up doing is figuring out how to run that system and how to maintain that system. So our study basically tries to talk to practitioners to sort of qualify this notion. And we did get a good view of that. And the other thing we tried to bring to the table from an academic point of view is that most of the research papers that you will find, I already mentioned Google, tend to come from large corporations. So we don't have a lot of evidence of what non-large companies do in practice. And so that's what we could bring with this study done in this setting. The conversations that we had, or how we extracted the data from experts or practitioners, is we looked through this framework. It's been presented in various forms by Patrick and manual. You're looking at how people run their data pipelines or how they tend to manage data, specifically for machine learning workflows. Of course, you have the model training, and then you have the deployment and monitoring aspect. And then we also looked at techniques or how practitioners actually manage the entire pipeline of the entire workflow. So this was the framework of discussion, and now what I will do is present the results in terms of practices and the tooling that is used in all these phases of this process. So we begin with this data management patterns. Of course, we didn't drill so deep as we did the framework presented. Now we'll get in terms of data pipelines and how they are actually working through this. But we tried to get an overview of how do these guys actually manage data that is particularly managed by machine learning workflows. And we structured this in terms of we discussed about storage and version controlling of the data. We noticed there's also a sense of abstracting the data when you're doing machine learning, and we'll discuss why. There's documentation of the data, and then there is data quality issues that crop up. So storage of the data is quite obvious. Of course, every company has the way it stores data. Either you're buying it from third parties or you have your own, let's say, storage solutions. But from a machine learning point of view, what came up is that it's very important to think, especially when you're dealing with neural networks, where your data actually sits. The reason for that is that it may constitute a large part of your training part of the time. So if you're fetching data from, let's say, network, and the machine learning training part is complicated, then you add an I/O aspect that tends to consume a large part of your compute time. So it became clear that some of the times you need to figure out a much more efficient solution to how to store the data in close proximity to the compute resources, and not just streaming it from S3 buckets, for example. The other thing is that the coupling of data from model images. In some cases, we did see that companies have an image that contains the data and the model itself, but the result of that is that you end up with build times that are pretty slow because of having data within the same image as the model itself. The other thing here is about version controlling data. I saw a graph here that showed version control running through the entire workflow. It's not a very trivial thing to do in certain data sets. When you have certain tabular data, for example, text data, it's quite easy to do, but if you have video images, and very large, you have to think of creative ways how to sort of version control this data. And most of the time, you have to come up with metadata of the data and version control that metadata, because it becomes almost not so obvious how to version control speech and things like that. The data abstraction part, this speaks, especially for large companies, that data sits in various silos, and the data scientist has to work with all these different data sets. So what we saw is some efforts to try to abstract these data sets so that you're not dealing with CSVs from this side, and you're not dealing with Excel files from another team, and so on and so forth. So what the platform team tends to do is come up with this standardized interface, for example, using XDF or Apache package, so that the data scientist can consume an abstracted data set and can emit the same abstracted data set, and another team can actually carry out the deployment of the model. So it facilitates a lot of a fair share of portability of your system, especially if you want to test your frameworks, if you want to move the data to a different, not the data, but the model into a different cluster. So if you have sort of this abstracted data set, data formats, that tends to be a bit easier to achieve. Documentation of data is something else that seems to be an issue in large companies, in the sense that, again, if you have data seated in different parts of the organization, let's say the organization has an insurance arm, it has a consumer finance arm, the data scientist usually does not know where to get the data for a static model that they want to build. So for that reason, as a good practice, it was seen that some companies that have this figured out, they have sort of data catalogs which then can facilitate discoverability of data and allow the data scientists to easily figure out what sort of features can be extracted from which part of the organization. Yeah, like that. Data quality, this is an always open problem, irrespective of which type of machine learning you're doing. But some efforts to actually try to improve on it. We saw that in some cases companies have a dedicated team that takes care of the quality of the data. And that ensures also that the schema, the data is actually validated at various levels, the schema and the data itself. And this is done by people who are actually in charge of data quality aspects in a dedicated fashion. And then it's important also to define what data quality means in your domain. It was clear that it's not the same, obviously. If you're dealing with video data, if you're dealing with speech data, if you're dealing with data collected from web crawlers and so on, it means totally different things. And so for this reason, it was evident that there needs to be a clear definition of what good quality data means, that even if you buy it from that party providers, then you actually can stipulate what you're looking for in terms of quality metrics of the data. Training model evaluation. The type of things that we noticed is that transfer learning was a big thing that addresses neural networks. I've seen here the presentation by Emmanuel saying that it's one of the attack points that can happen. Actually, that never came up from all the interviews that we did, but I did notice that most companies, not most, but a fair share of them were using public models to actually motivate their own models, what was the old stuff, and then a few of them were using private models as baselines. And those that use private models, or let's say one reason why transfer learning was used a lot was the cost-saving measure. So if you have a large model that is trained for 2 weeks, for example, it was not necessary to be doing that on a regular basis. So what guys did is they have different cycles of training, 2 weeks, and let's say a much more shorter frequency of training. And that's the application of transfer learning. The other application is to avoid a cost. But the choice of public and private is more dependent on the availability of models that are actually available to you. Or I didn't hear any company that spoke about security, but that was a really nice big thing. Explainability of models is something that came up, and this was spoken especially from regulated companies' point of view. There are some companies that it's not enough to have a very good model with very good accuracy if you cannot explain how it achieved that. So for that reason, some companies actually forego very good models and opt to take heuristics, because if the regulator comes along and asks how does this decision come about, they can actually explain it a bit more in a straightforward way. So in this case, they use these models more as a benchmark to see how much off they are from like the best possible model they could achieve. But for reasons of operation, for operating purposes, they use things like heuristics that are much more easy to explain. And then you have evaluation of models. So how do you tell that your model generalizes very well? We did see one company that had a very good solution to this. And what they've done is that they've stored data in different qualities, different levels of qualities. In the sense that the data is stratified that this data is really clean and can give you a perfect model. This data is half clean, this data is like not so clean. And so when they train the models, they are able to see how it performs across these data sets, for example. And what happens is that, of course, if your model scores very well on data that's super clean and scores very badly on data that's quarter clean, of course you don't need to do adjustments to the data. But at least it quickly tells you how well the model can generalize, even studying maybe not so clean data if it's open to the public. Frameworks, network architectures, and things like that. The question here was, so how do you choose your framework? let's say you want to build a speech model. You have, of course, you can choose Python, you can use TensorFlow, you can use the CAL framework. And we did find some organizations that are actually in the same space in terms of models that they're trying to build, but use different models. So that might be the question, why different models, why different frameworks? So, and most of the time is, if the CTO is very well versed with the framework, they will choose the framework that they feel gives the most flexibility. In terms of, if I want to tweak certain parameters, certain hyperparameters, very low-level stuff about the model, they know where to go when they need to tweak that. Others will choose it based on maybe the underlying computational engine. For example, if it's NKL or implemented in C++ compared to another one implemented in another Fortran. So in some cases, the sort of technical team is very opinionated on why a certain library makes more sense than another, especially for performance reasons. And of course, something else to consider is the architecture of the neural network. For example, if you think about the REST network, there are so many variants of it that you could use. So in that case, you ask them, why did you choose this one and not the other one? We'll see that later. Performance is a big issue when it comes to that. One neural network might perform much better than the other one because of the resolution of the images it consumes, and maybe it's tweaked, the layers have been tweaked in a different form, so that informs this choice of the neural network. And then there was this issue of experiments. How do companies actually track experiments? It was mentioned already by somebody that notebooks are not useful at some point. You have so many experiments you need to run. So how do you manage it? As you will see, there are very many different ways to do this. There is a tool called MLflow. At the time when we did the study, not so many companies actually use this. I wouldn't say it's not structured. They have a structured way to manage the experiment, but in different ways. You would imagine that there is a nice tool to do that, but actually not everybody uses the tools that you actually imagine them to use. Yep. And deployment and monitoring, this is a topic that I closely follow. When you talk to practitioners, what are the main issues that you try to capture when you deploy? You model and monitor it, and when you consider monitoring. So latency is a big thing, and the after fact that we had with a lot of developers is you need to start considering it much more earlier than you do in practice. So when you're choosing your architecture, when you're choosing sort of the stack, you need to already start to consider how to get very good latency. Improving it later on is a much difficult task. So for that reason, you need to bring it early on in the game. And it means, for example, choosing the protocols that you're using to serve. Are you going to use gRPC? Is REST sufficient? Things like that have to be decided pretty much early on. Yeah, I think I've already covered that. Monitoring for model staleness. This is what was called drift. Of course, it can happen in different ways. And this is very complicated to do in production. Particularly concept drift. We did see some cases or demonstrations where there is no good way to do it, especially if you cannot store the data that you're getting for inference. It's not that trivial to actually determine if your model is drifting. But from a research point of view, the topic on calibration, model calibration, comes to address sort of this issue in production. And then infrastructure utilization. From a software perspective, we normally, when we think about performance and improving and scaling, it's usually quite straightforward to scale horizontally most of the time, provide more resources, and then you're good to go. With machine learning, it's not necessarily the case. For example, speech recognition systems. If you're supporting a real-time speech recognition system, and you get a payload longer than you would expect, it tends to hit a node, and it's not obvious that scaling horizontally, providing a new node, actually would solve that problem. I don't know if I'm clear with that, but the idea is that in some settings in machine learning. For example, object detection, of course, you can send an image. If you get more images, you can scale, and the new images can go to new nodes. But in systems like real-time speech recognition, it's not that obvious that horizontal scaling would actually solve the problem. And so, still an open thought and an area of research how to actually scale in some of these machine learning use cases. And if we think about the entire pipeline now you've done your data management, you've deployed, and now you need to think about repeatability of this whole process. And in some cases, some companies have very, very elaborate ways how to do that. In other cases, it's a very manual process, end-to-end, just tweaking everything every day. But the lessons learned here is that version control, as we saw in one of the previous slides, is something that should cut through all the stages of this process. So in an ideal setting, you want to start with infrastructure as code, and end up with deployable containers. So everything can be replicated, everything can be traced back, and things of that sort. The other thing that we noticed is that encapsulation of every stage of this workflow into independent containers wherever possible. So that will facilitate, of course, automation. And if you think about teams that are highly distributed, that will increase the efficiency in terms of collaboration among the team. So, but building scalable pipelines in reality is not trivial either in machine learning settings. But there's a lot of effort how to do that. Of course, we've seen tools like Cell.co, which can be used in this case. But oftentimes this means you must adopt some form of container orchestration platform. Yep.
Did someone in Finland actually use Cell.co?
Yep.
Okay, cool.
Yep. And Sweden as well. So, yeah, so scalable pipelines. Scalable pipelines are, in a basic sense, it means, of course, if you have Kubernetes or you have Cell.co, something that allows you to actually orchestrate and manage this entire pipeline, if it's already containerized, then you're on to something that is scalable. And then, of course, if you're thinking about the entire pipeline, you must be able to test all the container images for integration, as we'll show here in one of the pyramid pictures. And one challenge is how to keep all these tooling up to date. There are so many tools that you need to manage. How do you keep them all up to date and keep your stack up to relevant?
Sorry.
Yep.
Can you go back 2 slides from there?
2?
Yeah. This one.
This one?
Yes, this one.
Yeah.
Because you mentioned that, like, in terms of using infrastructure, like scaling horizontally doesn't solve the problem. Do you mean like the case where the input can come as a stream in real time
Sure.
and the length of the stream is unpredictable, or do you also mean, like, let's say it's about applying like variable length of audios but reasonably bounded, like let's say within 5 minutes, and it's just a matter of like distributing that would not even be solved?
The case that was explained was the first one.
Okay.
So you get a hit on the endpoint, you have no idea when it's going to end, and for some reason it just keeps going. So then you have sort of this imbalance in your nodes, and it doesn't make sense to actually just provision a new one. So,
have there been like strategies considered of like chopping off the stream in some sense? It's kind of like say, okay, you can only stay on one node for like a minute, and then after that the next like minute minus 5 seconds goes to the next node or something to be able to like, do you know like some things that have been tried just as a curiosity, or?
No, but the use case here was maybe causing the problem because it was a UI tool.
Oh,
so,
okay.
So in that sense, the feedback is quite. There's sort of some real timeness in sort of the feedback that the user needs.
So like switching nodes.
It's just not. Yeah.
Okay, interesting.
However, sometimes we have data which is good enough to do the real-time processing, and sometimes we need to schedule because it cannot be give you the answer in real time. So did you see any example in the infrastructure utilization that they were handling both cases at the same time?
If I understood your question, so the capabilities to handle real-time and batch processing.
Yeah, that was it, exactly.
No, majority of the time there was usually one use case.
There was only one
Yeah,
case.
batch or online.
Or online,
Yeah.
not together.
Not together. Yeah. Okay. Yeah, I think all of them are. Actually, when we set up the study, to scope sort of the discussion, the team had to bring one use case, even if they had multiple models. We had to confine them to sort of one use case. Yeah, so we were just about to now look at the tools. Now, I'll just show you sort of, it's easier to just look at the distribution. If you have time, you can look at the paper. But here what we try to do is to go for sort of what platforms we are using in terms of storage. As you can see here, AWS is quite popular amongst the companies, followed by Azure and Google Cloud, and then we had one on-prem sort of setup. This is like a public, not a public company, but public service. So they're not allowed to be on public cloud systems, so they have an on-prem solution. And when you have such setups, there's a lot of information that is required to actually get your system up and running. What I want to maybe highlight here is when you look at the frameworks, in most organizations, you're using multiple frameworks to solve different things. That's how I put it. I mean, you rarely have companies just relying on one single framework. You use multiple frameworks for whatever achieves the solution that you're trying to shoot for. You're able to deploy the best framework for the task that you think can solve the task.
Could you investigate on the reasons like why different companies would use multiple frameworks? Because I can imagine a very large company might just because of the diversity of employees.
That's the main reason.
But like in a small company, you have a hard time imagining it.
Yeah. So the main reason, at least across all sizes, was that nobody is compelled to use a particular framework. So a data scientist should use the tools they feel that they are capable of using. For example, I think it was this case where I believe it's this one. Yeah, I think it's this one. Yeah, so this one, this is a chatbot system. So somebody could build a proof of concept with a TensorFlow framework, but they also still ended up with the production level using that. Some of these things dictated sort of the frameworks that we use. No big surprises when you think about version controlling, but the interesting thing is that at least when we did this, this sort of started to come up as a potential solution. So there was this sort of version control picture we had earlier, but Git is not suitable for everything in the entire workflow of machine learning system. Let's say machine learning workflows. It doesn't solve all problems in all cases, especially for data version control, and that's why this sort of shows up. This is sort of a dedicated tool that can actually version control the data and the models better, in a better way than Git would be able to do that.
When you say Git, you mean that Git self-hosted?
Both cases. Cloud, I mean, what do you mean?
No, because maybe I'm just like, but I've seen mostly Git being used like from GitLab, GitHub, Bitbucket. It's like basically a provider of the tool.
Yeah.
Git, I'm trying to picture what do you mean by
Yeah, so here we just asked them what sort of Git solution maybe do you use? So this is like classic Git. And then somebody will say, no, we use GitLab.
Okay.
And they have these opinions on it.
So nobody GitHub.
I would imagine some when they say Git, maybe GitHub.
That's where I was going with this.
Yeah. Yeah, so I just summarized Git related sort of this GitHub Git, which is sort of GitHub solution. So,
It sort of makes sense. I understand what you're saying.
GitLab, Bitbucket, these are also Git. GitLab, Bitbucket, these are also in a way using Git, right?
Yeah. But the solution.
That's why I was asking.
That's what I was asking. But my point is that, if you ask them, we didn't probe them why, but some are just opinionated that they probably like some aspects of GitLab that they wouldn't actually find in GitHub or something like that. For some reasons, it's legacy. They started that way. That's the culture.
Okay.
No particular. We didn't really probe it further why this is the case. But at least we try to understand any sort of structured solution in terms of version control. And at least in one case, this company, you can see that it has data and then it has a dedicated tool to actually cover data as well.
So the sample size of the companies is 10?
16.
16?
Yeah. So some that have not answered anything are not sort of in the distribution.
Are these big companies? What is the size?
Yeah, not all. So there's a spectrum of growth startups, but large of them are mature companies. I'd say 80% very mature companies. And actually also bears on the fact that the choice of tools is not, it's not associated with resources. It's probably a function of just what the developers are used to and what actually makes sense for their setup.
Sorry, was the question here about data version control or just version control, like code version control in general?
We probe for both. Did you ask if data or?
Yeah, are you asking here like what do you use for data version control?
Yeah.
And then they're answering GitHub, for example, and I guess they mean like large file storage.
We probed for what do you use all the sort of the stages of the workflow, and when they say that maybe they still use GitHub, then usually they're saying that they're collecting metadata and not versioning the data itself.
Okay.
Yeah. So then they're version controlling that file as a config file.
Okay.
This was also interesting when we tried to discuss about container orchestration. Of course, Kubernetes is quite popular, but then you still find bespoke solutions on how people decide to orchestrate their sort of containers. And this was because this is the same setup that is not allowed to be on public cloud, so they sort of are using OpenShift in their on-prem. But then you still have this sort of setups where they're using AWS Lambda or this Elastic container. In most cases, I think it was mentioned by Patrick, if they're already in a certain environment, there is no need to go looking for other solutions. So they're just using what the cloud provider has provided. In most cases, this is the reason. Machine learning training workflows. So this is I think what we try to capture here is the concept of scheduling your machine learning, ML training part of the workflow. So interestingly, most of the companies have some custom solution. We do have a dedicated tool set that would be really good for this. For example, Apache Airflow, Argo, but you still find most of the teams actually have written their own solutions to orchestrate and regularly retrain the model. Or sometimes it's just basically manual. So it's a script that's always run manually, retrieve the new model, you have new data, and things like that. Not so many of them have automated solutions to manage their training workflows. Experiment tracking, which I mentioned earlier. A lot of different solutions we saw. Somebody's basically collecting metadata, just storing that in some cloud solution. A few of them were already using Flow, virtual Synta, variance in sort of what kind of solutions people are using.
I think that these machine companies were, the problem they were solving, how complex the problem was, as compared to from one to another.
I'd say, I already say 50% of them were neural networks, already, and quite complex business problems, I think. Complex meaning extracting data, for example, from PDFs. Yeah. So you have OCR models there. You have computer vision models in there. Speech recognition models were quite complex in the sense that they were being used in healthcare. If I would try to give some context, without saying the companies. So they were quite, I'd say, fairly complex problems they were solving. I don't think there's one that had a very basic problem. Yeah. I mean, it's subjective here, what maybe you mean by complex, but I think they are fairly complex problems. Trading, I mean, getting new prices from the market and things like that. So, yeah, I didn't mention the business cases because, of course, we're in Finland, we probably figured them all out. But it's fair to say that, very, very good, decent problems to solve with machine learning.
None is the favorite preference solution.
As it seems. But all are equally confident of their selection. Repositories, same thing here. Very different solutions. As you can see, it's quite popular. The Stranium model, put it in an S3 bucket. Downstream will use it the way they want to use it. But in some cases, as interesting as Postgres.
But, sorry.
Yep.
I'm just interrupting you.
Yeah.
But the data platform actually, like, it's not doing other things. Did you find out that someone is using a data platform to take the data there and,
Yeah, somebody was using exactly Snowflake as their main data platform, but mostly to query data for machine learning training. And once they trained the models, they were storing the results in batch back to Snowflake, so that other parts of the organization could actually use the data.
I didn't see it there, I think that.
Yeah, but the model is not stored in.
Okay,
Snowflake.
model is not stored.
Yeah, so this is purely what do they do with the model once they train it. Deployment and monitoring. I think here there's not much to say, but what I'd like to highlight is something as mundane as monitoring. You still see people they tend to just collect logs and store the logs somewhere. Instead of, say, having elaborate Prometheus Grafana setups, people are just basically collecting logs. I guess it provides more transparency to later on if they need to follow up on something. But the common understanding is that Prometheus Grafana is not maybe the solution for everybody. And I think it's still in machine learning perspective, it's still a very open area to figure out what's the best way to actually monitor machine learning models. It's not enough to monitor the endpoints, but there's much more going on for an ML endpoint than just checking the traffic and the hits. So probably it's the reason why people are just collecting logs and storing them in another solution.
Did you ask about why? Because I'm curious if it's related to the data format or the kind of predictions that we have, for instance. Because I'm guessing, like, if you're in Prometheus and you're asking Prometheus, like, please log this image, how it goes through my GAN generated, it's probably not something out of the box.
Yeah, I think at least the main answer that we would get is that, it's not sufficient for a use case. It's not sufficient for a use case.
Okay.
So, yeah, that's one of the main points. it just doesn't serve our purpose.
Okay. So I'm guessing like there's a federal scripts
Yes.
being written and
Exactly.
it's like to the surface.
Yeah, and putting them in Elasticsearch, and then they can do whatever they want with it.
Mm.
Yeah. So the main problem, I think, if I would summarize, this is the problem. It's just too much to contend with in terms of tooling. From an architect point of view, you have to make decisions and sound decisions to choose from all the solutions. That if you think about data management, there's just so much you can use out there, but what actually works for you is still something you have to explore. And this is the current state of MLOps right now. And we probably think it's going to consolidate at some point. For example, if you look at the experiment tracking, I cannot now figure it out the way it is. So MLflow should be somewhere here, the experiment tracking. So already this is pulling up as one de facto solution. So sooner or later then we'll probably have something that's much more dominant in each of these segments. And then we'll have sort of so what they have in DevOps now, things are standardized in DevOps. In MLOps, probably things will get standardized once these tools emerge as dominant in their own segments.
And you got the question earlier, like if we had a lot of MLOps cases. This is why. Like they call, they say, oh yeah, this is interesting, let's work with you. We are looking for an expert in tool 73. Yeah, it's hard. You know?
Yeah, that's the reason why Valha is there in multiple boxes, we cover all of it.
But do you think
they want multiple of them?
Yeah. I was just wondering if Valha would.
Yeah, it's in multiple boxes.
Yeah, but you see yourself dominating sort of one space.
This is kind of focusing on the parts, and we are maybe dominating the end-to-end. So it's kind of, we are not trying to dominate, like for example, serverless deployment. MLflow is
Experiment management.
yeah, kind of like management and maybe like tracking to some point. DVC is data version control. Valha is kind of covering all of that from end to end. So kind of Valha is all about the pipelines, building a pipeline from beginning to end.
And also maybe there's one box missing or it's too tiny. Orchestration.
Yeah.
Maybe that's good. That's what Valha is good at.
Yeah. That's what many of the others are not doing. They are not doing orchestration.
Yeah, it's a major problem in the industry. It's been overlooked, but it's good.
Yeah. I think MLflow is also moving into pipelines as well.
I'm guessing they're trying to move everywhere because it's basically Databricks building and then also.
Yeah. So yeah, that's the business case for MLOps. Yeah, I think that pretty much summarizes my whole study, and then I encourage you to take a look at it. It's an easy read actually. It's not very technical. It's quite easy to read for the weekend. Yeah, so too many tools to deal with. As we've seen, the workflows and pipelines, they vary so much depending on the company, and particularly depending on the way of machine learning that they're working on. And then you have to contend with this issue. If you're a practitioner, do you go for integrated tools? For example, SageMaker, which has everything, or do you compose your own solution? For example, what is done with things like Valha and other solutions. But all in all, of course, you need to consider the flexibility of your own pipeline. And then longevity of the tools, something that needs to be thought about when you're using your pipelines, and how to decouple the small tools within the pipeline so that you can actually replace them much easier when you do. So yeah, I think that's pretty much what I had to share today.